Good morning, guys. We're trying something different today with some video notes. Welcome to 3.8 Newton's method. Newton's method is a technique for approximating the real zeros of a function, and it uses tangent lines to approximate the graph of the function near the x-intercepts. I'm going to draw some pictures for you to try to explain sort of how it works. Imagine that you had a curve, and that's what's pictured here, and you knew at least one value on that curve. And so that is going to be our first point, this x1 comma f of x1. You could construct the tangent line to the curve through that point. And if you did so, you would use this equation. Y minus y1 equals m times x minus x1, our point slope. Specifically for this particular function, that would mean f of x1 as your y1. Your slope would just be the derivative at the coordinate x1, and we'll leave that notation as it is. So our point slope form specific to this example is what I've listed here. Okay, if you were to look at that tangent line, then you could consider where the tangent line crosses the x-axis. And as you can see in the picture, we've labeled that point x2. So x2 comma 0 is a point on our tangent line. And as you can see, it's fairly close to the actual x-intercept of the curve itself. But we can continue this process to get a closer and closer approximation. Let's go ahead and figure out a way to express x2 in terms of the x1 and f of x1. So if x2, 0 is a point on my graph, then I could plug those two values in as my y and my x and see what happens to my equation. In other words, if that coordinate is on my graph, then I could put a 0 here, and my derivative times, and this x then will become x2 minus x1. And solving for x2, right, I could divide on both sides by the derivative. And that would give me, right, those two would cancel out. I would have to add the x1 to the other side, and I would have this equation. x2 equals x1 minus f of x1 over the derivative at x1. And that puts x2 fairly close to the x-intercept. What Newton's method does is it says to make this an iterative process. So what I can do, let me grab a different color here. What I can do then is say, okay, well, now let's take x2 and find its value on my curve. And I can construct another tangent line and do this process again, right? And so what's going to happen is that the x-intercept for that tangent line is even closer to the x-intercept of the curve. And I could continue this process, grab another color here. I could take that, maybe we called it x3, and I could construct its tangent line. And if you notice, the x-intercept of that tangent line is even closer to the x-intercept of our curve. And so Newton's method says to take this iterative process, meaning that we just repeat the process over and over again, and we can write the equation for this as x sub n plus 1. So the n plus 1 meaning like the number of times you've done the process. So we notice here x2 was after the first process, x3 would be after doing it twice, and so on. So x sub n plus 1 is equal to x sub n minus f of x sub n over f prime of x sub n. And so that's our formula, if you notice here, for Newton's method. Realistically, you wouldn't need to use this because in order to calculate, you would need to use the graphing calculator. However, if you were programming the graphing calculator, this may very well be how they come up with the approximation of their zeros when you have functions that aren't so simple to work with. So right below there, we've talked a little bit about where it comes from. That's for you students who enjoy knowing sort of the proofs of things and why things come about. Realistically, you just have to know how to use it. So imagine that you have a function, and it's a differentiable function in an open interval containing a value c. Then you can approximate your c. Notice here they're saying f of c is 0. So you can approximate your x-intercept by making an initial estimate and then using that formula that we just derived to come up with the next best estimate. And then you just reapply and reapply.